Section 1 Introduction. In this introduction, we discuss the importance of the optimizer choice in training deep learning models. The optimizer can significantly impact the speed at which the model learns and the quality of the results it produces. Some of the most commonly used optimizers include stochastic gradient descent, SGD with momentum, and adaptive gradient methods like ADAM. Adaptive gradient methods have an advantage because they can automatically adjust the learning rate for each coordinate, which can lead to faster learning with less need for hyperparameter tuning. However, these methods often don't perform as well as SGD when it comes to generalization. Recent studies suggest that the lower generalization performance of adaptive optimizers may be due to their stability, which can lead the system to settle into sharper minima than SGD, resulting in poorer generalization performance. In this study, we propose that the generalization performance of ADAM can be improved by incorporating an exploration strategy. This strategy could help the optimizer escape from sharp minima, similar to the role of exploration in reinforcement learning. We build on a previously proposed framework that uses a buffer to store a limited history of gradients from previous iterations, known as critical gradients, CG, during training. This method can be seen as a form of momentum that allows the optimizer to overshoot and escape narrow minima. However, the original proposal for memory-augmented adaptive optimizers, particularly ADAM using CG, has a problem known as gradient cancellation. This occurs when new gradients have high directional variance and large norm around a sharp minima, causing the aggregated gradient over the buffer to vanish and preventing the optimizer from escaping the sharp minima. To address this issue, we propose storing critical momenta, CM, during training, which leads to a new version of ADAM that can effectively escape sharp basins and converge to flat loss regions. We illustrate this with optimization trajectories on a 2D loss surface corresponding to the Goldstein price, GP, function. We observe that ADAM converges to a low loss but sharp region of the surface. ADAM combined with sharpness-aware minimization, ADAM plus SAM, converges to a flatter but higher loss region than ADAM. Memory-augmented variants, ADAM plus CG and ADAM plus CM, bring more exploration, and only ADAM plus CM is able to find the flat region that contains the global minimum. We also provide a pseudocode for ADAM with critical momenta, ADAM plus CM. Our work makes several key contributions. 1. We introduce a framework for promoting exploration in adaptive optimizers. 2. We propose a new memory-augmented version of ADAM, which stores and leverages a buffer of critical momenta from previous iterations during training. 3. We illustrate on a wide range of synthetic examples how our method addresses drawbacks of existing memory-augmented methods and promotes exploration towards flat minima. 4. We observe empirically an improvement of the generalization performance of different deep learning models on a set of supervised language and image tasks. Section Summary. The choice of optimizer used in deep learning models significantly affects their performance. While adaptive gradient methods like ADAM can achieve fast convergence, they often result in worse generalization performance compared to stochastic gradient descent, SGD. In this work, we propose a memory-augmented version of ADAM that stores critical momenta instead of gradients, allowing the optimizer to escape sharp minima and converge to flat loss regions. Our method promotes exploration and improves the generalization performance of deep learning models on various tasks. Section 2 Related work. In the field of deep learning, many optimization techniques have been developed to enhance the speed of convergence and improve the overall performance of models. Stochastic gradient descent, SGD, with momentum has proven to be effective in certain situations, but it often necessitates meticulous tuning of learning rates and convergence criteria. On the other hand, adaptive optimization methods, which adjust the learning rate for each parameter based on past gradient information, have achieved top-tier performance in many supervised learning problems. These methods are also more resilient to changes in hyperparameters. ADAM, an optimizer that combines momentum with an adaptive learning rate, has become the preferred choice for a wide range of models and tasks, especially in large-scale deep learning models. However, ADAM has been criticized for its lack of generalization ability, leading to the development of several variants. One successful approach to improve generalization performance is to converge to flat minima. For instance, sharpness-aware minimization, SAM, enhances model performance and reduces sharpness within a specific neighborhood during training. Since its introduction, SAM has been used in various applications, improving generalization in vision transformers, reducing quantization error, and enhancing model robustness. Several techniques have been proposed to further enhance SAM's generalization performance, such as altering the neighborhood shape or redefining the concept of sharpness. Efforts have also been made to reduce its cost, primarily by reducing the need for the double backward and forward passes required by the original algorithm. Memory-augmented optimizers, which store gradient-based information during training to enhance performance, represent a balance between performance and memory usage. Different memory augmentation optimization methods have different memory requirements. For example, stochastic accelerated gradient, SAG, and its adaptive variant, SAGA, require storing all past gradients to achieve a faster convergence rate. While these methods offer significant performance benefits, their high memory requirements often make them impractical for deep learning. Alternatively, one could use only a subset of past gradients, as suggested in limited history BFGS, LBFGS, its online variant, OLBFGS, and stochastic dual coordinate ascent, SDCA. Memory-augmented frameworks with critical gradients, CG, use a fixed-sized gradient buffer during training, which has been shown to provide a good balance between performance and memory usage for deep learning compared to previous methods. In our study, we aim to further enhance CG by storing critical momenta instead of critical gradients. This approach leads to improved generalization performance in adaptive optimizers, particularly ADAM. Section Summary. In this section, the authors discuss various optimization methods for deep learning models. They mention that while SGD with momentum is effective, it requires careful tuning of hyperparameters. Adaptive optimization methods, such as ADAM, have shown state-of-the-art performance by adjusting the learning rate based on past gradient information. The authors also introduce memory-augmented optimizers, which store gradient-based information during training, and propose a new approach that stores critical momenta instead of critical gradients, leading to improved generalization performance in adaptive optimizers like ADAM. Section 3. Memory-augmented ADAM. In this section, we'll be discussing our method, which is an extension of the memory-augmented framework. We'll be focusing on the ADAM optimization algorithm in a supervised learning context. The standard way of updating parameters in ADAM can be explained as follows. 1. We calculate the moving average of the gradients, denoted as m_t, and the squared gradients, denoted as v_t. This is done by taking a weighted average of the current gradient, g_t, and the previous moving averages, where the weights are determined by the decay rates beta_1 and beta_2. 2. We then correct these moving averages for bias, resulting in hat m_t and hat v_t. 3. Finally, we update the model parameters, theta_t, by subtracting a fraction of the corrected moving average of the gradients. This fraction is determined by the learning rate, alpha, and the square root of the corrected moving average of the squared gradients plus a small constant, epsilon, to prevent division by zero. We also introduce the concept of critical gradients, CG. To enhance ADAM, we keep a fixed size buffer of priority gradients, G_C, in memory during training. We then apply an aggregation function over this buffer to modify the moving averages. The selection criterion for the buffer is the L2 norm of the gradients. The buffer is structured as a dictionary where the keys are the L2 norms of the gradients and the values are the gradients themselves. The keys are decayed at each iteration by a decay factor, lambda, to encourage buffer updates. If the L2 norm of the current gradient is larger than the smallest key in the buffer, the corresponding gradient in the buffer is replaced by the current gradient. A common choice for the aggregation function is to add the current gradient to the average of the gradients in the buffer. However, we've noticed that combining ADAM with CG doesn't always yield good results. We believe this is due to a phenomenon called gradient cancellation. This happens when the gradients in the buffer are quickly replaced by high-magnitude gradients when the model parameters are near a sharp minimum. As a result, the buffer quickly fills up with high-variance gradients whose average tends to zero, allowing the learning process to converge. This can cause the model parameters to oscillate within the sharp minimum, as any attempt to escape is thwarted by the incoming gradients in the buffer. We illustrate this phenomenon with a simple example, where we show the buffer gradients and their average, as well as the new gradient, within sharp minima where ADAM combined with CG gets stuck. More plots illustrating this can be found in the appendix. Section Summary. In this section, the authors introduce a method called Memory-Augmented ADAM, which extends the ADAM optimization algorithm by incorporating a memory buffer of critical gradients. The buffer is updated based on a selection criterion and an aggregation function. However, the authors observe that combining ADAM with critical gradients can lead to the problem of gradient cancellation, where the buffer quickly converges to high-variance gradients that cancel out the new gradients, preventing learning from progressing effectively. Section. Critical momenta, CM. We've observed that the gradient cancellation in ADAM plus CG can make it difficult to escape from sharp minima. To address this, we've developed a new approach that uses a buffer of critical momenta during training, which we denote as M_C. Similar to previous methods, we use the L_2 norm of the gradient as a priority criterion. We avoid using the alternative M_T_2 as it would slow down the buffer's update speed. Our buffer is structured like a dictionary, where each key value pair is G_C_2 M_C. Each key has a decay factor lambda, which is between 0 and 1, that is applied at each iteration. This integration of critical momenta results in a new algorithm, Atom plus CM, which updates the moment as follows. The moment at time t, denoted as M_T, is calculated as a weighted sum of the previous moment and the current gradient. The weightings are determined by the parameter beta_1. The updated moment, M_T, is then the sum of the current moment and the average of all critical momenta. The updated variance, V_M_T, is calculated in a similar way, but with the square of the sum of the current moment and the average of all critical momenta. The weightings in this case are determined by the parameter beta_2. The update rule for Atom plus CM is then given by the following. The updated moment and variance are adjusted by the respective beta parameters raised to the power of t. The updated parameter, theta_t plus 1, is then calculated by subtracting a fraction of the adjusted moment from the current parameter. The denominator of the fraction is the square root of the adjusted variance plus a small constant, epsilon, to prevent division by 0. When we're at a sharp minima, the elements of the buffer are quickly replaced, but the variance remains low due to the momentum term's inertia. The quick change in gradient direction results in smaller new momentum terms, which have less immediate impact on the buffer's aggregate value. This allows for an overshooting effect, which aids in exploring and escaping sharp minima. The larger the buffer, the stronger the overshooting effect, and the wider the minima must be for learning to converge. This is because the learning process needs to stay in a minima's basin long enough to fill most of the buffer before it can return to the minimum it jumped over and allow the optimizer to converge. We've observed this behavior empirically. Section summary. To address the issue of gradient cancellation hindering the ability of Atom plus CG to escape sharp minima, the authors propose a new approach called Atom plus CM. This approach leverages a buffer of critical momenta during training, which is updated using the gradient L2 norm as the priority criterion. By integrating critical momenta, the new algorithm allows for the overshooting effect to still happen, enabling exploration and helping to escape sharp minima. The size of the buffer affects the strength of the overshooting effect and the convergence of the optimizer. Section 4 Insights from Toy Examples. In this section, we'll be discussing our findings from a series of experiments we conducted using simplified tasks. Our main goal was to test our hypothesis by comparing different combinations of the Atom optimizer with memory augmentation and sharpness-aware minimization. Firstly, we looked at how critical momenta can encourage exploration. We compared the optimization paths of Atom combined with critical momenta, CM, Atom alone, Atom with sharpness-aware minimization, SAM, and Atom with conjugate gradient, CG. We used simple, non-convex 2D loss surfaces for these comparisons. We also tested a combination of Atom with both SAM and CM. To add to the Goldstein price function, we used the Ackley function, which has a nearly flat outer area with many sharp minima and a large hole in the center. The global minimum of this function is at the point 0, 0. We minimized the Ackley function using 10 different starting points and compared the paths of the different optimizers. Each model was run for 500 steps, with the learning rate reduced by a factor of 10 at the halfway point. We used a grid search over the hyperparameters for each optimizer to find the best performing setup. Our observations showed that only the CM variants were able to explore the loss surface, resulting in a lower loss solution. We have included additional trajectories with various different starting points for both the Ackley and Goldstein price loss surfaces in the appendix. Next, we wanted to compare the implicit bias of the different optimizers towards flat regions of the loss landscape. We evaluated the solutions based on the final loss and sharpness, averaged across 20 seeds. As a simple measure for sharpness, we calculated the highest eigenvalue of the loss Hessian. Our results showed that Atom combined with CM found flatter solutions with a lower loss value compared to Atom alone, Atom with CG, and Atom with SAM in both examples. We also found that Atom and Atom with SAM reached almost equal loss values for the Levy function with a negligible difference in sharpness. However, for the GP function, Atom with SAM converged to a suboptimal minimum with lower sharpness. We believe that the buffer size controls the amount of exploration, and we have analyzed this empirically in the appendix. We also investigated the ability of the various optimizers to escape from sharper minima. We used a class of functions with two global minima. a flat minimum at the origin and a sharper minimum at the point 1, 1, 1, 1. We found that ADAM mostly converged to the minimum closest to the starting point. However, ADAM with CM converged to the flatter minimum more often than ADAM with CG, regardless of the starting point and degree of sharpness. To quantify this bias in higher dimensions, we sampled 50 different starting points uniformly in a 10-dimensional space. We then counted the number of times an optimizer found the flat minimum at the origin by escaping the sharper minimum. Our results showed that ADAM with CM, with a buffer capacity of 20, had a higher escape ratio than the others as the sharpness increased. We repeated this experiment with various buffer capacities in the appendix. Section summary. In this section, the authors validate their hypothesis by comparing different combinations of optimization algorithms on toy tasks. They analyze the optimization trajectories and observe that critical momenta promote exploration and reduce sharpness in the loss surface. They also find that ADAM plus CM, ADAM with memory augmentation and critical momenta, performs better in terms of finding flatter solutions with lower loss values compared to other optimizers. Section 5 Experimental Results. In this section, we'll share the results of our experiments. Our aim was to test our method on complex models and benchmarks. We've averaged all our results over 3 trials. First, we looked at language modeling. We trained a single-layer long short-term memory network, LSTM, on the Penn Tree Bank, PTB, dataset. To evaluate the performance, we reported the validation perplexity on a set of data that we didn't use in training. We trained all models and optimizers for 50 cycles. We trained the models for 40 cycles, similar to previous studies, and we reduced the learning rate at the 25th cycle by dividing it by 10. We reported the results after performing a grid search over corresponding hyperparameters. The details of this grid search are in the appendix. We found that ADAM plus CM always converges faster, suggesting that it has explored and found a better solution than other optimizers by the 18th cycle. The second best performing optimizer is ADAM plus CG, which reaches lower perplexity after reducing the learning rate. However, both CM variants overfit after convergence. Next, we tested the effect of ADAM plus CM on different model sizes for image classification. We trained ResNet models, specifically ResNet 34 and WRN1, with 40 layers, for 3 different trials. We compared optimizers in terms of the validation accuracy computed on a set of data that we didn't use in training. We trained the models for 100 cycles, reducing the learning rate at the 50th cycle by dividing it by 10. We summarized the results from all experiments performed for image classification tasks, where we reported the best validation accuracy achieved by different ResNet models when they were trained on CIFAR-10/100. We reported the results both with and without performing an extensive grid search over hyperparameters. The details of this grid search are in the appendix. In each case, we found that CM variants perform best. Without grid search, CM variants perform best on both datasets, with ADAM plus CM achieving the best results with the ResNet 34 model, while ADAM plus SAM plus CM performs best with the WRN1 model. With grid search, ADAM plus SAM plus CM yielded the best validation accuracy for CIFAR-10, while ADAM plus CM performed the best on CIFAR-100. We observed that CM variants have slightly faster convergence in WRN1, and ADAM plus SAM plus CM outperform other baselines when the learning rate is reduced after the 50th cycle. We also found that using a large buffer size can further reduce the sharpness of the solution in such complex settings. Section summary. In this section, the authors evaluate their method on language modeling and image classification tasks. For language modeling, they train a single-layer LSTM network on the Penn Tree Bank dataset and compare different optimizers. They find that ADAM plus CM converges faster and achieves better performance than other optimizers. For image classification, they train ResNet models on CIFAR-10/100 datasets and again compare different optimizers. They observe that CM variants perform the best, with ADAM plus CM achieving the best results for ResNet 34 and ADAM plus SAM plus CM performing the best for WRN1. Section ImageNet. We also decided to train an efficient Net B0 model from the ground up using ImageNet. To do this, we utilized a publicly accessible efficient net implementation in PyTorch, with a weight decay of 0.0001 and an initial learning rate of 0.0001. This learning rate was then reduced by a factor of 10 every 30 epochs. More details about the datasets and models we used can be found in the appendix. We compared the top 1 and top 5 accuracies on the validation set. Due to limitations in computing power, we stuck with the default set of hyperparameters. We noticed that the combination of Atom W and CM, centered momentum, converged faster and achieved better final top 1 and top 5 accuracies than the other optimizer baselines. However, SAM, sharpness-aware minimization, didn't perform as well under the default hyperparameter setting. Our analysis supports the claim that Atom plus CM finds a flatter surface containing the global minimum. This is evident from the top right plot showing lower sharpness compared to Atom or Atom plus SAM. It also shows that parameters travel a greater distance during training when using CM, suggesting that CM encourages more exploration than the other optimizers. The bottom left plot reveals that buffer elements stored by Atom plus CM have lower variance during training compared to Atom plus CG, conjugate gradient. To compare the agreement among buffer quantities, we selected the element with the highest norm within the buffer, calculated the cosine similarities with other elements in the buffer, and then took the average of these similarities. The bottom right plot shows that the agreement in Atom plus CM remains higher than in Atom plus CG. This suggests that the aggregation of buffer elements in Atom plus CM will more often result in a non-zero quantity in the desired direction. Conversely, high variance and disagreement among elements in the Atom plus CG buffer may lead to gradient cancellation during aggregation, resulting in behavior similar to Atom. Section summary. The authors trained an efficient Net B0 model from scratch on the ImageNet dataset using a publicly available implementation in PyTorch. They compared different optimizers and found that Atom W plus CM performed the best in terms of convergence speed and final accuracy. They also analyzed the behavior of the optimizers and found that Atom plus CM explores the parameter space more and has better agreement among buffer elements compared to Atom plus CG.